we will continue, and it's my pleasure to introduce the next speaker for the first plenary talk. The Professor Mário Figueiredo is well known in the community, but he's a full professor at IST, University of Lisbon. He's internationally recognized for his research work in machine learning, image processing, and analysis and optimization. He's a fellow of EuroSIP, European Association of Signal Processing, since 2020, fellow member of IEEE since 2010, fellow of International Association of Pattern Recognition since 2009, and in 2019 he joined the Academy of Science of Lisbon, Portugal, as a corresponding member. I will not talk about other papers and publications of his curriculum and prizes. It's very extensive, but he's recognized as one of the world's most influential researchers, and including the highly cited researchers list released by Clarivate Analytics. So his talk will be about artificial intelligence, historical aspects, modern applications, and implications. So it will be certainly a very interesting topic. And at the end of his talk, we'll have time for some questions. So please, Professor Mário, go ahead.
Thank you, Sergio. Let me begin by saying that it's a pleasure and to be here. I've been attending CONFTELE for many years. Thank you for organizing and for inviting me. Can I share the screen? And thank you for your kind words. Can I share the screen?
Yes. Yeah.
Oh, yeah. Okay, it's already. I think it's this one. Yeah. Is it visible? Can you see it?
Yeah, yes,
sure.
Yes.
Okay, good, thank you. So when I was invited, I spent some time thinking about what I should talk about. And I hesitated between a more technical talk or something more entertaining and more historical, and I decided for the second choice. And so I'll be giving a sort of an overview talk about artificial intelligence, focusing on historical aspects, how we got here today, where we are. Try to exploit some connections that are not so often mentioned. And then I'll go over a few modern applications and implications for society in a very brief overview way. So it's not a technical talk, it's kind of try to be more entertaining than technical. But I hope you learn something from it. I always learn a lot when I try to do these things because I have to explore, so it's a good opportunity. So of course, an obvious question is, what is artificial intelligence when we start talking about artificial intelligence? And of course, this question of what is artificial intelligence immediately begs the question of what is intelligence, by the way, itself, artificial or natural. And this is a very tough question. There's no consensus about what intelligence is. And if you look it up on a dictionary or on Wikipedia, you'll find words like ability to do logic or abstraction or understanding or learning or problem solving, reasoning. And of course, it's complicated. There's no consensus even among philosophers and psychologists and people who study intelligence. All we know is that we have this little piece of meat inside our heads, which weighs approximately 1.5 kilos, that has 100 billion, like 1,000 million neurons, 300 trillion connections, and that does something that we feel like intelligence, and that we call intelligence. So this gentleman here is Potter Stewart. He was a USA Supreme Court judge or justice, as they say, in the 60s, and he's sort of famous because he came up with this sentence when he was trying a case of the state of Ohio against the owner of a movie theater because he had shown what was supposedly arguably a pornographic movie. And when he wrote down his decision, he said, well, I'll not try to define pornography, and maybe I could never do it, but I recognize it when I see it. And why am I saying this? Because this is sort of the same approach that Alan Turing, the famous Alan Turing, took when he was trying to reason about intelligence. He said, I will not try to define it, but I'll recognize it when I see it. So he wrote this very influential paper in 1950 called Computing Machinery and Intelligence. Essentially what it says is that if it acts, reacts, and interacts as an intelligent being, then we call it intelligence. I will not try to define it, I will recognize it when I see it. So there's parallel between these two these two definitions, or these two ways of avoiding having to define something that we know we can recognize when we see it, but we can't really grasp, can't really define in a very precise way. And this is, of course, intelligence is one of these things. Of course, I'm sure you all heard about the Turing test. It's an imitation game. It's the idea that if you have a person and the computer interacting with another person by questioning and answering and establishing a dialogue, if person C, who is giving the test, cannot distinguish if A and B, which of them is the computer and which is the human, then we have to say that the computer passed the Turing test. There's a lot of criticism, though, so there's a huge controversy, a lot of philosophical debate about the definition of intelligence, about the validity of this test. One of the most famous arguments is the famous Chinese room by John Searle, right in the 80s. I will not go into details of what this means. So the idea that maybe you can act as intelligent, but inside you actually don't understand anything that you're doing. So in that case, it would be hard to call you intelligent. But I will not go into that. I'll just call your attention to the fact that this is an ongoing debate and study. Of course, there's no consensus. It's a very active area of research in this area. And even at places like Google, can you see my pointer? Is it visible? Yeah. So even at Google, you have people researching on philosophical and conceptual aspects of intelligence, what intelligence means, like François Chollet, which you may know from other things. He's a famous machine learning researcher. And in this famous paper that came out a couple of years ago, he says like intelligence measures an agent's ability to achieve goals in a wide range of environments. And both things are very important. Not only achieving goals, because achieving goals is something that a very simple machine can do, and you do not call it intelligence. But a wide range of environments is a very important aspect for something to be called intelligent. And this is a definition, a synthetic definition by Legg and Hutter, Marcus Hutter, who reviewed a big chunk of literature on definitions of intelligence and measures of intelligence, and summarized it in this very, very synthetic sentence. So François Chollet proposed a set of tests that kind of try to get at human intelligence, tests that are not easy for machines to excel at, such as which essentially involve not only answering something, but also understanding what the question is, which is something that machines are not very good at. So for example, here, if you're given these three first examples, you immediately see that the correct answer to this first problem is identifying which object has a larger number. So you have 3 of these blue guys and 2 of the red ones, so the answer is this one. Here you have 3 of the reds and others, so it's the red. A machine would have a very hard time understanding this because it has to somehow guess what is being asked, not only answer a question which is very well posed. So these kind of things. So François Chollet proposed a set of tests like these and a few more sophisticated, which will try to aim at what humans can do and machines cannot yet do, at least very well. So going now to artificial intelligence. So artificial intelligence, there are, of course, lots of definitions. It can be seen as simulation of intelligence by machines. Of course, that begs the question of what is intelligence. It's a behavior of an artificial system that humans see as intelligent. So kind of external validation. It's a system that perceives the environment and takes decisions towards a goal. And we have lots of examples, of course, old examples such as game playing machines, chess playing machines, the famous Deep Blue that beat Kasparov. I'll go to that, talk about it in a minute. The machine that won the Watson TV show game in the US. Of course, the machine that learned how to play Go and beat the best human players. Of course, we have self-driving cars. We have medical analysis done by machines nowadays, image processing, image analysis, medical diagnosis, very detailed medical diagnosis in different areas. I'll come to that later on. But of course, in a sense, if you take these definitions too seriously, like a system that perceives the environment and takes decisions for the goal, in a sense, the thermostat is also an intelligent system. because it perceives the environment, it measures the temperature, and takes a decision turning on or off your heater to achieve a goal, which is keep your room at a cozy temperature. So all these definitions are very loose, and sometimes you can fit things that match the description, but you don't see as intelligent. So this is trying to come up with precise definitions is a very delicate issue. Of course, nowadays we all know that in a sense, social media and the brains, the engines behind social media are intelligent because they behave intelligently. They try to show you what you want to see. And so there's of course, these systems which we all see in a sense, if you think a little bit about it, as being intelligent. They sense the environment and they take decisions what to show you to achieve some goal, of course, which is profit. What is the genesis of this? So it's typically seen that this conference in Dartmouth in 1956, which had very, very famous people, which I'll mention briefly in a second, which was apparently the one where the expression artificial intelligence was proposed by John McCarthy. So this conference had no less than 4 Turing Awards: John McCarthy, Marvin Minsky, Alan Newell, and Herbert Simon. Herbert Simon actually also won a Nobel Prize, in economics. And of course, in the middle, there's Claude Shannon, which we all know and love in telecommunications. So he was also there. So Claude Shannon is also at the birth of artificial intelligence and modern machine learning and artificial intelligence for several different reasons. And I'll mention his name a few more times. So this is a very important event that happened like more than 50 years ago, 60-something years ago. Of course, these people built their ideas on the shoulder of previous giants, for use expression by Newton. All the mathematicians and logicians and people who work in this idea that machines can compute, of course, are the roots where these people built their ideas. So the first applications of artificial intelligence were games. Okay. So right in the early 50s, even before that, but in the 50s, Arthur Samuel at IBM built the first checkers playing program in a computer, one of those old IBM computers with tapes. And a pretty famous philosopher called Hubert Dreyfus said, he was very skeptical and said, okay, computers can play checkers. Checkers is simple, but no computer will ever beat a human chess player. So he said this in '65. He was himself a good chess player. And 2 years later, he lost a game of chess against an old computer, a Mac X6. So this is the first example that it's very dangerous to make these bold predictions and bold assessments, because most of the time you'll be proved wrong very quickly. Of course, in '97, we all know this. So the IBM Deep Blue beat Kasparov, and there are also game-playing machines that deal with games that have some randomness in them, like backgammon. So this early interest in games was rooted in the idea that a human that is intelligent should be very good at playing these games. So there was this parallel between being good at these mind games, not mind games, intellectual games, let's say, that require intelligence and artificial intelligence. So if you could show that a machine is good at these, this is the path towards building artificial intelligence machines. Of course, chess, let me say a little bit about chess. So the number of possible chess games is of the order of 10 to the 120. This is an estimate produced by Shannon, interestingly, which is much larger than the number of atoms in the universe. So you cannot solve the game in the sense that you cannot try all possible decisions that you can take at any time. And so very quickly, Shannon wrote about chess playing machines, interestingly, in 1951. Of course, you have to do non-exhaustive search. You have to try only a few possibilities. You have to have heuristics to evaluate their positions and so on. And so this led to the development of all these chess playing programs and chess playing actually devoted hardware, dedicated hardware, which ended up in '97 with Deep Blue that defeated Kasparov, as we said. So this is just an example of how computers were very influential in chess games. So in a very different front, which is the cognition and perception vision front, which was happening at the same time. People were trying to understand how the human visual system works. And so first, very influential work was, well, of course, in parallel with other people, but these are very famous, Hubel and Wiesel, They wrote and they sort of understood the neural basis of vision. They came up with this model for the visual system, for the visual cortex neurons, and sort of understood how these filters are stacked. And they ended up winning the Nobel Prize a few years ago. I think I had the Nobel Prize. Yeah, they won the Nobel Prize for this work. And at the same time, or even a little earlier, McCulloch and Pitts developed the neuron model, which was the first sort of mathematical model of what a neuron is like. Essentially, that's something that sums up the contributions from other neurons that are connected to it, and then this sum is above a threshold, it fires. If it's not, it doesn't fire. So this was work that was being done around the same time that people were developing chess-playing machines. These people were working in these areas. These two areas were completely disconnected. So artificial intelligence was one thing. This was like nothing to do with artificial intelligence, although they later, of course, converged, as we all know. So this led to very, very strong optimism, which revealed to be extremely premature. So in a very famous book by Herbert Simon in 1965, he wrote this sentence: "In 20 years, machines will do any human task." Of course, we all know that's not true. And Marvin Minsky wrote, "Within a generation," so this would be like in 1990, "the problem of creating AI will be solved." Of course, it's not true again. So this premature optimism was actually, sometimes it went to very extremes. So like when the first artificial neural network was created, which I'll talk about in a second, there was this very interesting article on the New York Times saying that the author of the article, the journalist, was saying that Dr. Rosenblatt, talking about the work of Dr. Rosenblatt, who's the creator of the first perceptron, first neural network, artificial neural network. He was saying that in 1958, that perceptrons would fire to planets as mechanical space explorers. So he was already predicting very, very far ahead, and it was, I'd say, premature optimism. And then, as usual, premature optimism leads to disillusion. People were not very excited about what was happening, and some negative works started to come out. So a very famous work here was a book called Perceptrons, written in 1969 by Minsky and Papert. Actually, interesting, Minsky is the same guy who wrote this other book that argued that within a generation the problem would be solved. So this actually was a book with a negative view of neural networks, because they were seen as sort of competitors. So he didn't believe in this neural network approach. He believed in the symbolic approach that was being exploited for games, for playing games and to take decisions in that very different approach. And there was a very famous report in the UK called the Lighthill Report in '72 that claimed that the discoveries made so far have not produced the promised impacts. So these were very negative views of what was happening in artificial intelligence and in neural networks. So these two most largest streams of work in this area. And that led to something, a very different change of paradigm, which started appearing in the '70s, which was called expert systems. So maybe you've heard about these, most of you, or many of you, I'm not sure. So an expert system was something that's very fashionable in the '70s and in the '80s. And the idea was that you could have, with the help of experts on some topics, say doctors, you could build a knowledge base about some subject, say how to treat some disease. And then a user would query the system, would query the knowledge base using a user interface through some inference engine, and you would get advice from the knowledge base, which had been filled by the expert. This is called an expert system. So this led to the development of specialized languages for these, like Lisp and Prolog, dedicated machines. There was these Lisp machines. We had one at IST when I was a student. And there was a huge investment in this topic, in this area. So 2/3 of the Fortune 500 companies had some sort of expert systems in-house, and they were widely used in the 80s, especially in finances and for all sorts of decisions. Japan made a huge investment in this direction. So they had this national project to build a 5th generation computer, which was a computer built specifically for these kind of systems. But things didn't work out so well. So it lasted for about 10 years, from 82 to 92. Then they abandoned. And then the real bottleneck is that everybody was underestimating the difficulty of making explicit the knowledge and building a knowledge base from the knowledge of experts, it becomes extremely hard, and it's a very underestimated problem in terms of difficulty. And so by the end of the 80s, or mid 80s, end of the 80s, all of these companies that had invested in these, they went bankrupt. The companies that built the systems went bankrupt or were acquired. And so this was a sort of a 10-year adventure that was not very successful. And so this led to the so-called second winter of AI. So, so here we have the first winter that I mentioned with this early disillusion that things were not so fantastic as they seemed to be. Then there was the second boom, which I just talked about, which is the expert system boom. And then things didn't work out as fantastically as people thought they would. And then in the middle of the 2000s, say in the late 90s, or I might say the mid 90s, things started accelerating again, but in a different trend, essentially by resorting to machine learning. So machine learning had existed before, but it was not seen as something that could be used to build, say, expert systems or artificial intelligence. It was seen as something else. It was like signal processing or image processing. It was for analyzing patterns, not to do reasoning, not to build intelligent machines. Just to put things in historical perspective, let's see what was happening in the world around this time. So late 80s was the generalization of the personal computers. So the IBM PC, I think, appeared in 1982 or 83. Of course, that was not generalized for at home, but in the late 80s, early 90s, a lot of people already had personal computers, and certainly in universities, almost everybody had a personal computer in the 90s. So the internet is born in the late 80s, or generalized, I'd say. This is the end of the USSR, so this is the end of the socialist Soviet bloc. And in the 90s, we saw the appearance of these very, very famous companies. So sort of roughly in this order. So Amazon, and then Google, and then Facebook, then YouTube, then Twitter, and of course there's a lot more. And I will say a little bit about what is the connection, what is the synergy between the appearance of these companies and the boom of machine learning and AI. So nowadays we have all these autonomous weapons, vehicles, deep learning, we have AlphaGo, we have a lot of social excitement and also concern about artificial intelligence and machine learning. So, by the way, what is machine learning? I'm sure most of you know what machine learning is, but let's define it. It's an area of study. I like this definition by Arthur Samuel, the same guy who wrote the first program to play checkers. It's the area of study that aims at making computers able to learn without being explicitly programmed. So it's a very good definition. So the question, the key thing here is that unlike in an expert system, you don't have to ask an expert how to do something. So the computer will learn from examples. And this is a key thing. So at the intellectual and also technical root of machine learning, we have Norbert Wiener, which I'm sure most of you know who he is. He's one of the great mathematicians of the 20th century, no doubt about that. And if nothing else, you all know the Wiener filter, I'm sure, if you've done signal processing. But most importantly for what we're seeing now, he formalized the concept of feedback. He was the first person to kind of mathematically formalize the concept of feedback loops and control. And he wrote this extremely influential book in 1948 called Cybernetics, from which we now got the word cyber from cyber stuff, cyber world, cyber media, cyber this and cyber that. And he has this very nice sentence at the cover, which was extracted by someone, the person who designed the cover, which has, this is a study of vital importance to psychologists, physiologists, electrical engineers, radio engineers, sociologists, philosophers, mathematicians, anthropologists, psychiatrists, and physicists. And this idea that this was a very high level conceptual tool that was as important to electrical engineers and to telecommunications people as it was to psychologists or to philosophers is kind of very original at the time, because all these areas were sort of separate. And he thought, no, there's this very encompassing way of seeing, which is control and communications. So communication is fundamental, because with no communication, there's no control. You don't know what's happening. And control theory is important because you want to control how things happen. And so this is an extremely influential book. Another anecdotal fact is that it was him who hired McCulloch and Pitts for MIT. So those people we saw earlier that created the first model of how how a biological neuron works. So he was a very, very influential person at the beginning of all of these machine learning phenomena. So Frank Rosenblatt, we already saw a few minutes ago, created the first perceptron. So the perceptron was this machine. Actually, I can show you the kind of the idea. Kind of very simple, a very simple neural network, just a one-layer neural network with a weighted sum of pixels, essentially, and that makes a decision. But what's new here, beyond McCulloch and Pitts and beyond the neuron model, is that idea that you can compare your decision with some desired decision. You have an error signal, then you can feedback the error signal to adjust the weights of the machine to make it work a little better. So this idea of error feedback, which is rooted in the work of Norbert Wiener, the idea of feedback for controlling, for improving your behavior, is fundamental, and it's an intellectual breakthrough in the middle of the 20th century, which allowed the explosion of machine learning. This idea of error feedback is the center of machine learning, of modern machine learning, and there are different instances of these. I'm not going to any. So Hoff and Widrow is also very famous. These people are also well known for adaptive filters in the electrical engineering side of things. So these are the beginnings of neural networks, and of course, this is the beginnings of machine learning, as seen from this perspective, or learning from examples. What happened in the following decades? Now I'm going to fast forward. So following the perceptron, we had Hopfield networks in the 80s. We had Sejnowski and Hinton with Boltzmann machine also in the 80s. Then we had in 1986 the sort of popularization of backpropagation. It had been proposed before, actually earlier, even in the 70s. The idea that you can use this idea that you can propagate errors backwards into the weights of the machine, into the parameters of the machine to make it improve. But that can be done across many layers, not necessarily just for the previous layer. This is a fundamental idea that's behind the advent of deep networks. And of course, the idea that these networks can be convolutional, so they can be shift invariant, which is very important for saving a lot of parameters. So you can improve the training a lot. And these two people, as you know, so Jan LeCun and Geoffrey Hinton won the Turing Award a couple of years ago, together with Benjo, for this for being pioneers in this area of neural networks. And in '98, a very famous program called LaNet5, which was developed by Jan LeCun for AT&T, when he worked at AT&T, which read with this automatic reading of digits for checks in banks, which was the first really successful practical real-world application of neural networks, specifically of deep convolutional networks. So this is 23 years ago this year. Okay, 60 years later, we have these kinds of networks. So these networks that learn from mistakes and that backpropagate their error. Of course, there's a lot more here than just that. We have Google DeepMind coming up with machines that can learn how to play games that are considered the most difficult games for humans, like chess, Go, and Chogi, which is sort of a Japanese version of chess. And it's very famous. You've all seen these. This has been in the news everywhere. It's Nature papers. They built these machines that learn how to play the games even better than the best humans. And in more modern instances of these, they actually, well, actually the 1 after 0, they learn without ever seeing a human game. They learn just from the rules of the game and playing themselves against themselves. And this is kind of the state of the art in game playing, which happened not through the symbolic reasoning that was pioneered by McCarthy at the beginning, but by putting neural networks inside these machines. Of course, I will not go into that. So what are these deep networks? I'm sure you all know. So these deep networks became very famous. It's considered a landmark year is 2012 here, where there was this competition for image recognition, for classifying images. It's very famous ImageNet competition, or dataset if you want. In 1 year, from 2011 to 2012, there was a huge improvement in terms of error rates, from 25% to 16%, with the introduction of this, one of the first famous deep neural networks, AlexNet. And then in the years that followed, so this performance became better and better and better. The networks became bigger and bigger and bigger. Now the best networks have hundreds of layers, and they have performances that rival the human performance in recognizing what's the semantic content of an image. So these modern networks have hundreds of millions of parameters. They are trained on millions of images. They require huge, powerful hardware, and so they're. But big companies have almost infinite resources, and so they do it. For example, all the images that we upload to Facebook are ran through several of these deep networks to do lots of classification tasks. Like, for example, to try to detect if there's a pornographic content in the image, it's automatically detected, and other things. So what changed so much in these deep networks with respect to previous machine, say, computer vision and image understanding, image analysis, is that during several decades, computer vision researchers spent a lot of effort trying to come up with ideas of what features should we extract from images that then, when fed to a machine learning classifier, would give you a good classification of the content of the image. How can I learn? How can I what should I extract from an image that allows me to detect that the image contains a dog? And this was completely abandoned in the deep learning world. And so I don't care what it is. I don't need to think about it. The machine will learn what the features are. So this is a fundamental word in deep learning, which is end-to-end learning, that the machine is learned from one end to the other. You don't have to design anything. Of course, you need to choose an architecture. So this is a bit of an exaggeration. You have to choose an architecture, you have to tune the architecture, but you don't need to decide a priori what features you will extract. The machine will decide what are the good features. And this is a paradigm shift in computer vision and in image understanding and image analysis. Of course, this also happened in speech recognition. So speech recognition had reached sort of a plateau in the early 2000s, in the late 90s. It had been improving. So this is word error rates in speech recognition. And with the introduction in the beginning of the 2010s, so the second decade of the century, so the performance started improving again very dramatically with the introduction of deep networks. And nowadays, not long ago, so the best speech recognition systems are at human level, or sometimes even a little better than human level, which is actually absolutely remarkable. Again, with the introduction with improvements in neural networks. So this picture is sort of a zoom of this part here. So the first deep neural network was introduced around 2011 for speech recognition, and then improvements, more data, improvements, and around 2017 they reached human level. So are we approaching biology? We started by looking at biological systems. So 2 years ago, the biggest networks had the order of hundreds of millions of parameters. So this is a picture that shows operations, the giga operations, doesn't really matter, and total top one accuracy in some problem doesn't really matter. I just wanted to look at the size. So it's hundreds of millions of parameters. That's the key thing. But to keep us very humble, I remind you that we have this very famous little worm called C. elegans, which has only 302 neurons. It's a very small little animal, and still it lives, it moves, it feeds, it reproduces, it interacts with other C. elegans around it, and it has only 300 neurons, not hundreds of millions. So this should keep things in perspective, that maybe the things we are doing with the artificial deep neural networks are extremely brute force, and are not, of course, they are certainly not using resources in terms of energy and in terms of hardware in the most efficient way, as we can tell by looking at biology. And moreover, these biological systems fit better the definition of what intelligence is, in the sense that they achieve goals. They do achieve goals. They survive, they reproduce, they eat, they move, and they do it in a wide range of environments. It may rain, maybe it doesn't rain. They adapt to conditions. And these machines that we've been building up to now do not adapt to a wide range of environments. A machine that plays chess can only play chess. Now, there's a few others now that play like 3 or 4 games, different games, but the level of adaptivity to changing environments of artificial machines is not even close to what biological, even the simplest biological systems can achieve. So now a brief overview of where did this come from? And when we want to know where these things come from, we should follow the money. Where are the business? What's the business that underlies these developments? So if we go back only 25 years ago, I'm sure you all knew that the internet looked like this 25 years. Not the youngest of you, but the ones that are at least as old as me or will remember that you had Yahoo, and you sort of needed to know what you were looking for to go look for things. The internet was sufficiently small that you could have a guide. You could have like a tourist guide for the internet. It's a famous book published I had one, of course, in '95 by José Magalhães, who was actually a pretty famous politician who was in the Portuguese Parliament, the Socialist Party. So he wrote this book called the Practical Guide for the Internet, which was kind of a list of interesting things to see in the internet. Now it would be, of course, completely impossible. And closer to our telecommunications context, so mobile phones look like this. So in 1995, this is a Nokia from 1995. So there were several technological revolutions that underlie this artificial intelligence revolution. One of them, of course, is telecommunications. Of course, so mobile phones, as you know, changed dramatically in the past 25 years. So a modern smartphone is an absolute amazing piece of equipment with more compute power than big computers had a couple of decades ago. Also in terms of communication, the communication devices that are inside and communication network infrastructure around the mobile phone is absolute. It's one of the most fantastic technological achievements of humanity. Of course, smartphone sales skyrocketed. Now we have more than 2 billion smartphones being sold every year. Of course, other types of things are going down. So even standard mobile phones which are not smart are just basically dead. Personal computers are stagnated. But smartphones are skyrocketing their sales. Of course, there are victims. There were interesting devices like digital cameras. There still are, but not as important. So the vast majority of pictures taken today are taken with smartphones. GPS systems, MP3 players, all of those died because smartphones have all of that inside. So another technological revolution is the internet, of course. Most of it, or nowadays, a lot of it on mobile devices. So this is the number. So this is up to 2016. So this kept on increasing. So it is just to show that there's an exponential increase of the number of internet users around the world. So these are huge numbers. So now I'll show you more up-to-date numbers in a second. So this is from 2018. So more than half of the population of the world has access to the internet. There are up over 3 billion actual users of social media on mobile devices. These are huge numbers that are hard to grasp. And of course, all these people that are using the internet, they have access, but most importantly, they also produce data in huge scale. They produce video and they upload it. It's somewhere in the cloud. They produce photos. They produce data about where they are, data about what they buy, what they purchase, what they search for in social media, what they like. So this creates a lot of information about a lot of people, about billions and billions of people. And so this is a huge opportunity for companies to explore this idea. So another technological revolution is sometimes called the big data revolution. So data is, again, the amount of digital data that's being produced in the world is, again, also growing exponentially. It grew like 50 times in the past decades. And this is typical of exponential, is characteristic of exponential growth. 90%, well, this number, I could adapt these numbers, it depends on the exponent, but 90% of the world's data was created in the last 2 years. And this will be true again in 2 years. So in 2023, 90% of the world's data will have been created from 2021 to 2023. So it's growing exponentially. And this is kind of how it is split among different things. So sensors are having more and more important fraction of the data that's being created. Of course, social media, most of it video, lots and lots of video, of course, voice over IP, and of course, enterprise data for companies. So just this is a very interesting picture that I found a few days ago. That this gives us the idea about the unbelievable amount of data that it's flowing on the internet. Most of it in mobile devices. For example, some numbers that are absolutely mind blowing. This is every minute. This is per minute. In 2009, per minute, 18 million text messages are sent. 188 million emails are sent per minute in the world. It's unbelievable. So this is a lot of data. I can share these pictures with you later. So what are the technological revolutions that are underlying this, or even deeper? If you look even deeper, so one of them is the cost of, and the availability of computer memory and storage. So the price of memory, of storage, either memory or disk or tape or whatever, it's all here, has been decreasing exponentially. So we talk a lot about Moore's law for computation, but this is not as often seen. The cost is going down exponentially. For example, if you go back like to the 90s, you would have like to pay something like $100 to store. That's the price of the media for megabytes. Now it's of the order of 10 to the minus $4 per megabyte, which is a unbelievable decrease. So it made things available. It's essentially not an issue anymore. You don't really think about storage problems. You just don't care. You can store whatever you want. Computation. So this is Moore's law, and 120 years of Moore's law. Of course, it's not exactly 120 years, but if you look at this, this is a plot that I like, because it's the vertical axis is graduated in computations per second per constant dollar, because this is very important. This is per second and per constant dollar, so without increasing the price. And we see that in the past 20 years, so from 95, from 95 to 2015, which was when this was available, we had a 1 million fold increase in speed. So the number of computations that you can make per second per dollar increased 1 million times in 20 years, which is no other technological device had this kind of explosion in performance. If we had cars that had improved like this in the past 20 years, it would be an amazing world where cars would cost like $1 and they could go for 1 year with a milliliter of gasoline. Of course, we're not there. So, but this caused a very interesting paradigm shift, okay? Because they have this super abundant contents. The content itself lost its value. No one wants to pay to have content that is you can get for free. And so the key thing, the value moved from providing the content, which was like TV networks, newspaper, websites, to searching. So searching became the key thing. So there's so much content in the internet that the important thing is to find what you want. And this saw the advent of Google with a very key idea. So the central idea is, how can you monetize search? How can you make money from searching? And of course, the key thing is publicity, because you sell publicity together with the search, and so you know who the user is, and you can target publicity to the interests of the user. And this is, of course, this is $1 million idea. Of course, that's why Google is such a huge company and hugely valuable company these days. And of course, there's also social networks. How can you monetize social networks? Again, publicity. And these are just a few plots. I don't want to spend a lot of time just showing how the amount of money that is generated by publicity in these companies. And there's yet another aspect, which is again supported on artificial intelligence, which is recommendation for online commerce. And we saw the appearance of Amazon and the explosive growth of Amazon. This is like a few years ago, and Amazon nowadays is bigger than all the retailers in the US. These big retailers, Walmart, Target, Best Buy, all of them together are significantly smaller than Amazon. So this was a huge change in paradigm in the business surrounding these areas. And what is this supported on? It is supported on this idea that you can use these devices and you can use the internet and the social media and so on to capture your attention, to capture the user's attention. And you can do it because you know the user's taste, his habits, his friends, where he is or she is, his activities, his orientations, political, sexual, religious. You know, the social media know a lot about you, and they can sell this information, and they can use this information to capture your attention. And this is very well characterized in this very nice book by Tim Wu. It's called The Attention Merchant. So your attention is captured and sold to third parties so that they can do whatever they want, namely fundamentally publicity. And this sort of a huge change in the panorama of what are the biggest companies. This is the global companies, where only in 2008 the big companies were companies that actually sold material things, most of them like oil, electrical machinery, and so on. Gas. We have Microsoft that sold, well, this is the first one, and AT&T that sold communications, but lots of these sell actual things or products. Now, in 2018, this is 2 years ago, the top companies do not, well, apart from Amazon, Amazon doesn't produce anything, they just sell things from other producers, but Microsoft, Google, Apple sells computers. Facebook doesn't produce or sell anything. And still, it's the 5th most valuable company in the world. It was in 2018, I don't know exactly what they are right now. But this change in the top 10 companies in the world is essentially thanks to the AI, internet, mobile communications revolution of the past two decades. Of course, all of this is supported in artificial intelligence, machine learning. I'll accelerate a little bit now because all of these systems, social media, recommendation, search, all of this is supported on AI and machine learning. So these are the sort of the scientific engines behind these new business paradigms. And if you look at these, we see that these companies are indeed investing hugely in research. Okay, for example, this is up to 2017. Amazon spends upwards of $20 billion per year in R&D, which is a huge number. So Google spent a little less and Facebook a little less in 2017. I don't know what the numbers are right now. And just to put things in perspective, the budget of the Portuguese Ministry of Science and Technology and Higher Education is 1.5 billion. So all of the Portuguese university, all of the Portuguese higher education, university, polytechnics, and all of Portuguese research, which is funded by the Portuguese state, is 1.5 billion, which would be something like here, okay, which is a small fraction of what these big companies spend per year in research and development. Of course, also in telecommunications, so machine learning and artificial intelligence are hugely central in telecommunications nowadays, not only on this side of things, because of course, we're interacting with the world, with connected things, with the Internet of Things, with the mobile users, with all of these. Of course, data is processed by machine learning and it's exploited by artificial intelligence on the separate, but also inside and I'm sure you all know a lot more about this than I do. This is a prediction of what will be the markets in the next few years, starting 2016 and up to 2025 in telecommunications for the use of AI technologies. And most of it's actually network and IT operations, monitoring and management. So it's inside the networks themselves. So AI and machine learning is also extremely important and influential inside telecommunication companies, not only as a tool, but also as something that's used inside. So let's get to the last part. So applications and implications. Of course, there's lots and lots of different applications of AI. There's, of course, good ones, and I'm going to accelerate a little bit because I'm running out of time. So you can use AI for good. This is an opening statement by Kofi Annan, the previous president of the UN General Assembly before Antonio Guterres, introducing this special issue of Nature about AI for good. How can you use AI for good? And he was talking about how data can be used to help end malnutrition across the world, and especially in Africa. And there are lots of very interesting applications of AI and machine learning in this area. You can fight poverty with data. One very interesting example is this image processing, image analysis tool developed by Joshua Blumenstock at Berkeley a couple of years ago to assess assess poverty levels across different areas of Africa by looking at satellite images, daylight and nighttime, and trying to assess the intensity of agriculture, the amount of daylight, the amount of electrical light that's there, and from there you can assess levels of poverty, and then you can give this information to governments and to non-governmental agencies to try and intervene there. And there's lots of work in this direction. Even Facebook had this huge project to map the population of Africa with the resolution of down to 1 meter. So nowadays there's a very, very detailed map of where populations in Africa are, down to the meter resolution. And this is extremely important in the case of for aid organizations and for local governments to help these populations. Of course, there's also AI for bad. I will not spend a lot of time. You've all probably heard about the Cambridge Analytica. This is a very good example of how AI can be used for bad purposes. I will just skip this idea. And this raises, of course, ethics. I like to mention this book from 1974. So Louis Althusser was a French philosopher who wrote this little book called Philosophy and the Spontaneous Philosophy of Scientists. And he was arguing that scientists, when they reach the limits of knowledge, they tend to become philosophical spontaneously. And this is happening in AI because AI is beginning to have a lot of influence and impact in our lives through many decisions. AI researchers are beginning to think about ethics a lot, and there's a lot of discussions around ethical AI. And the quintessential ethics problem is the trolley car problem. What should you do? Should you let the car go ahead and kill 5 people, or move it to the other line and to the other track and kill only 1 people? What should you do? How do you decide? And this is a key importance because of self-driving cars. Because self-driving cars will have to take decisions, and difficult decisions, such as the self-driving car, should it stop? Should it go ahead? So suppose you cannot stop. Should he swerve to the left and kill the woman, or should he go straight ahead and kill the man? And this is not clear what to do. Okay, or depending on who's in the car, and how many people, if they're old, if they're young, if they're men, if they're women, if it's there's a lot of these things. And there was this huge experiment done, this huge study, which is published in Nature a couple of years ago, which I like to mention because I think it's extremely interesting. And it shows that you cannot have a general purpose moral machine, let's say, that's valid in all countries, because the choices vary widely across countries. For example, if you go to Western countries, you have a tendency to spare the young over sparing old people. Okay, if you have to choose between running over a young person or an old person, in Western countries you have a preference for sparing the young, not running over a young person. But in Eastern countries, it's precisely it doesn't exist this preference. For example, so you cannot have the same type of decision built in a car, which is sold in Eastern countries or in Western countries, or in the South versus the North. So it's what people see as the right moral decision depends a lot on, of course, the society that they're living in. And so this is a huge impact in designing artificial intelligence systems that take decisions that have influence over people's lives. Of course, one of these areas is medicine. I could talk a little bit about applications of AI in medicine, but I will not do it because I'm running out of time. I'll just call your attention to the fact that here too there are lots of ethical aspects that need to be taken care of. For example, there was this interesting system that was built in China that, looking only at faces of people waiting in a waiting room, it can find out that some people have irregular heartbeats, so say atrial fibrillation or some irregular heartbeat. And this is done only from the images of the people. Of course, it raises the question, is this ethical? Can I diagnose a person without that person having given consent to be diagnosed? So all these issues are very key today. You can, well, I'll skip this in the interest of time. So now I like to show this example because these systems sometimes have very unexpected consequences. So do you have any idea? I'm not sure, so I cannot have feedback. So, but I would typically ask you that a couple of times. Do you have any idea what this is? This is kind of swing that swings a mobile phone. And why does anyone want to swing a mobile phone? Because in China, people can get a discount in their health insurance if they take 10,000 steps a day. So some clever people built this machine that just pretend that you took 10,000 steps a day just by swinging the cell phone on this little device. So sometimes by using these AI things and on the internet and the smart device that you have in your pocket, sometimes the human is smarter and can just get away from it and get. Of course, this is even more critical if you're starting to use AI for war engines. If you have just a machine that decides if this is an enemy or a friend and decides to fire, this must be done with a lot of care. And this is not science fiction. because in the US, this is being taken very seriously. So artificial intelligence is now being used as an essential component of defense and security strategy, as you can say. So if you search about this, you'll find a lot of interesting stuff. The National Security Commission on AI releases a report, so they're looking at these. So they have AI ethics committees at the Pentagon. Of course, the U.S. Military Advisory Board debates ethical issues of using artificial intelligence for military purpose. So if you have a machine that can decide whether to shoot or not to shoot, things become very, very tricky. And so this idea that you need ethics guidelines for trustworthy AI and for explainable AI, this is a very important topic these days. We have a very big ERC research project at the Institute of Telecomunicações by André Martins, which is specifically on this topic of explainable AI. How can we explain the decisions? And this is important if you're trusting people's lives with the artificial intelligence decisions. And so my last message is that to deal with the biggest challenges that the use of AI in society have, you need to train people who work on in these areas to be able to think critically about the human context in which they will be used. And so this means that students should have some background in philosophy and in ethics and in sociology and things that have to do with human beings. So at MIT, they took this very seriously. And nowadays, at MIT, even if it's taken an engineering degree or computer science, you have this HAS requirement. HAS stands for Humanities, Arts, and Social Sciences. And their argument is that this is an indispensable part of your undergraduate education. So HAS, so Humanities, Arts, and Social Sciences, provide you with the opportunity to deepen your knowledge in a variety of cultural disciplinary areas and practical critical thinking. So critical thinking is an absolutely fundamental aspect of education, because we don't want to end in a world, as I'm sure you've seen this sentence before, 2001, where the computer that's controlling the spaceship says, "I'm sorry, Dave, I'm afraid I can't do that." So when the machine will no longer obey and will have its own goals and will decide what to do independently of its human creators. Thank you.
Thank you very much, Mario, for your excellent presentation. We are on time, but I think we have some time for a couple of questions from the audience. While someone is not raising the hand, I will ask you, how do you think that artificial intelligence can play some role in, for instance, in applications for industry, or nowadays we have this industry 4.0 with all the sensors, IoT. You think this can be applied? Are the platforms strong?
Oh yeah, I think it's already being applied in a lot of industries. So I teach a machine learning course, a PhD course in machine learning, and the students have to do projects, and I have students from different areas, and every year the projects I ask them to suggest a project, and every year I'm surprised because I learned that artificial intelligence is being used in yet another area I didn't know it was being used, like design compilers for computer science, or in civil engineering to study the behavior of some bridge, or there's no area, at least at the research level, there's no area that's immune to machine learning, and because everywhere you have to analyze a lot of data and make sense of it, so that you want to take the best decisions from what's happening. There's an opportunity for machine learning and AI to be used.
Professor Salema, you want to put?
Yeah, well, I think Mario has already elucidated us in a number of ways. I wonder if you know of, or you can tell us a little bit about some applications of artificial intelligence to the everyday problems in telecoms, like, for instance, propagation in a mobile environment, which is a hell of a difficult problem with thousands, more than millions of situations, and we are always trying to find out what is the best way of getting a solution, or another way to put it is, where is it possible that we can not get a solution, and there's no way to solve the communication problem.
Yeah, well, I don't know. That's not my area. I don't know a lot about it, but I know it's being used, and I've been in say master thesis with people who are using machine learning, for example, for channel planning and channel sensing and things like that. So every time you have a decision problem which is too hard to solve analytically, you can train a deep network to do it. It doesn't always work, but typically it does. And then we've seen even nowadays applications of, say, deep networks in areas that was sort of surprising. Like, for example, in fluid dynamics, which is not exactly the same as Maxwell's equations and their propagation, but it's a related area because it's also governed by partial differential equations. So in fluid dynamics, there are very difficult problems, like in predicting what are the flows of some fluids in some complicated structure, like to design propellers or wings and stuff like that. And people have found that you can train neural networks that find the solution. And it's not very clear how they do it, but they do it much faster than trying to solve these PDEs numerically. So there's a lot of impact. This was very unexpected because 10 years ago, no one thought about this. So there's a very important impact of deep neural networks and machine learning in scientific computation, in replacing things such as finite elements and things like that are typically used. Now you use just a big neural network, you give it solutions that were computed that take a long time to compute. The neural network, after it's trained, it's very fast to give you the solution, and then you can change. You can change the wing, or you can change the propeller and see what the fluid is. So I'm sure something like that can be done for telecommunications. I'm sure probably Carlos Fernandez, I'm sure he knows about applications of artificial intelligence and machine learning for, say, designing antennas, complicated antennas with complicated shapes. I'm sure machine learning is being used there. I don't know any details, but I'm sure it is.
Okay, thank you. We have a question from Fernando Pereira.
Is there?
Okay, thank you very much, Mario. Just a comment and a question. Professor Stelema was asking about telecommunications. I can tell you that, for example, today in coding, image and video and point clouds, MPEG, JPEG, everything is about deep learning. So yes. Coding is deep learning in these days. But my question to Mario was about the ethical issues. So what we have in these days, for example, at IST, we have this ethics board, and many of the questions were about data. Okay, for example, biometrics, about the data. So do you think that very soon we will have to ask permission not only to collect the data, but for the time of operations we will do with that data with machine learning? So it's a little bit like genetics, not only about the data, but what we would be allowed from the ethical point of view to do. And we would have to ask permission not only to capture or use the data, but we would have to ask permission to process the data in a certain way using deep learning technology.
I think so. I think it should. I think a good example of that is the example of the waiting room, where you have the people. If you ask the people permission so that they can capture their images, they would say, yes, okay, I'm just sitting here, why can you capture my image? But what they're not telling you is that they're actually assessing if you have some heart problem, and you don't know that they're doing that, and maybe you don't want people to know that you have that heart problem. Or there was another example that I skipped, was that you can diagnose some diseases from speech. We have people at Technico that does that, like Isabel Fincoso works on that in her group. You can diagnose people for several diseases such as Parkinson's just by analyzing your speech. So maybe you're calling your insurance company, and on the other side, they're recording the call, and later they will try to see if you have Parkinson's or some early signs of Parkinson's, and maybe they will increase the premium that you have to pay for your health insurance. So this is delicate, right? So what they do with your data using deep learning is, and maybe even in a few years, they will be able to do more things that they don't know that they can do right now. And so I completely agree. I think.
Yeah, but the examples you gave is still very much about the permission to capture the data. It's about the privacy thing. I was thinking more about precise, but you do good things. I was thinking more about doing bad things, but
But this one, I think it was a bad thing. If you use my voice to find out that I have early signs of Parkinson's, and then you will increase my insurance premium, like the cost of my insurance, that's a bad thing because you're using information that I didn't give you about some potential disease that I may have, not to cure me or not to help me, but to charge more because I'm at a higher risk of having the disease. And I didn't allow you to use my data to do that diagnosis. I just spoke on the phone with you, the insurance company. So yeah, so if I would say like when you call a company nowadays, you have this call will be recorded for quality reasons, blah blah blah, right? And you have to accept, or otherwise you hang up. I think in the future they will say something. This call will be recorded and will not be used for any other purpose than to just know what you have to say. We will not use it to diagnose your diseases. We will not use it for anything else, or to assess your emotional state. Nothing. That's so. I think so. I think that's a very. I think you raised. This is a very important aspect that you raised. Yeah.
Okay, thank you. We have a question, a final question from Sergio Macho.
Hello. Thank you, Professor Mari, for this very interesting talk. Again, a comment, because we all have contact with machine learning in intelligent artificial. In our area where we work with array antennas, there is a new recent literature of new techniques using exactly deep learning for generating the meta surface and generating the radiation patterns. So this is a completely alternative way, and we need to adapt for this. So this is actually in the same way that you're saying. And the question about the final comment that you said, that machine learning will continue to make decisions, and maybe as you increase in the complexity, do you think as a byproduct some will come with intelligence, or this is
somewhat, sorry?
Some conscience, like someone there's some discussion about the revolution of AI, the dangers of AI. I know that role as
my personal position is that it's not clear, not yet, not soon. There's no philosophical reason, there's no essential reason why a machine cannot have consciousness, at least in my view, because, well, there's lots of arguments for that, but my perspective is that it's in a very, very far future if that happens. It's not anytime soon. We're very far away from that. But it's not essentially impossible, and that's what I would like to say. But we have no idea how to do it. No one does.
Okay, thank you very much. I believe there will be very much more interesting questions, but we already delayed 10 minutes for the next section. And so I would like to thank you again for your excellent talk and pass to the next section. Thank you very much.
Thank you.
I also would like to inform all the attendees that the Zoom session will last for one morning or one afternoon. So after 1 p.m. In the afternoon, we will change the Zoom section. So you have to log in again. So during from 1 p.m. to 2 p.m., we will have some videos about our sponsors and patrons. Thank you very much. Armando, please.
Hi, hello to everyone. I hope that you are listening me well. I'm going to share this special section on optics, photonics, and quantum effects. We have 4 papers in this section. The first one is going to be presented by Sara Mantei from IT Aveiro and University of Aveiro. The second one from Orlando Frazão from the Next Tech Porto. And the third one is from Tiago Morgado from IT Coimbra, the University of Coimbra also. And the last one is going to be Maurício Ferreira from IT Aveiro and the University of Aveiro. So I think that they are quite interesting, in fact. And one curiosity, all these papers have experimental work. So I am very pleased with it, because I am still from the time that when we put a section on optics, most of the work was theoretical work. I'm nothing against about theoretical work, but it's quite nice to see that nowadays there are really a lot of experimental work going on optics and